All right, so once again, the thermodynamics is we're building on the concepts right now. So we're still studying heat, and we know that the heat is a form of energy that flows from hot to cold. And so we're still going to be looking at this relationship to the mechanical energy of the molecule. We're going to bunch of observations. It's 120 degrees outside, and these women are wearing something black. Does that help or does that hurt in terms of maintaining a steady body temperature?
It should,
so you guys,
should absorb more.
Yeah, I mean, you're going to heat out faster, right? Give yourself a phone. So you're going to heat out faster. You will feel hotter. So that's certainly not going to help if you're wearing something dark. I mean, you guys live near Houston, so when it's really hot outside, wearing something dark means that it's going to absorb more heat. You're going to heat out faster. Yet these women claim that they feel cooler. So the question is there some kind of a heat-induced hallucination, or is there a reason for it?
I think they capture wind, right? Those outfits.
Okay, cute. Austin, where'd you get that from?
I saw like an old documentary about, or it was something included on a video that showed like in the Middle East they would wear.
Okay, yeah, there's a I'm going to give you 20 points because number one, you watch something and then you find something interesting enough to remember it. I mean, being from Turkey, which happens to be a Middle Eastern country, I mean, these people cover their bodies because of religion, obviously, but the religion says nothing about the color that you have to use. And there's notice that in extremely hot locations, there's a strong preference given to black colors. And the reason why they wear black is because they say it's going to make you feel cooler. So the question is why? And the wind has something to do with it. That's actually correct. So the question is how. All right. And once again, another thing which is related to colors, this is not so much colors, but the stuff that we sent out into space, notice that we have reflective surfaces on. So why do we use reflective surfaces on the equipment that we sent out into space? Is it because we're trying to impress the space aliens, or is there a better reason for it? Obviously, there's a reason for it that we will have to look into. All right, so those are the main things. Okay, we'll investigate.
In the 1950s, we discovered the spectacular stunt known as Marvellous Inferno. This man, known only as Marvello, will attempt to beat the heat while lying in the middle of a raging bonfire. First, he has himself entombed inside a wooden box. The box is then covered with high flammable packing material, then surrounded by dry wooden boards. Next, it's all saturated with gasoline, the high-octane stuff. The torch is lit and thrown onto the pile. It explodes into a blazing inferno with Marvello stuck right in the middle. Firemen stand by ready to move in and extinguish the flames, but Marvello has given strict orders to wait until a signal is given. And so far, it hasn't been given. Finally, the fire crew gets the go-ahead, and not a moment too soon, the blaze is about to consume everything, including Marvello. They put out the fire, but are they in time, or is Marvello toast? Look, he's still in there. The firemen place a damp towel over him, but there's no sign of life. Wait a minute, he's getting up. He's all right. Let's hear it for the marvelous Marvello. Another seeing is believing classic. In the 1950s, we discovered the spectacular stunt known as Marvellous Inferno. This man...
Okay, so 5 reasons as to why this guy was okay. Okay, guys, if you think of any reason why this guy was perfectly safe, go ahead. Just tell me. This guy is perfectly safe because... All right, so there are 5 reasons as to why this guy is perfectly safe. I had a firefighter once taking my class, and he could just go through like 5 of them just like that. Okay, yeah, average heat sealed. Obviously, that wasn't one of the reasons that I was thinking of, but obviously it helps, right? So give yourself 5 points for it. Okay, and so we'll just go over each and every one of them shortly. Number 1, he's underneath the fire, so that certainly helps, not above the fire. So that's, and then because the heat goes up, they give yourself 5 points. That's one of the reasons. And there are other reasons that we will focus on. He's in a wooden box. Why not be in a steel box or something? Would that help? Would that hurt? Fire burns fairly quickly. There's by design. So that certainly is going to help, right? So the question is why. And all right, so a bunch of stuff that we'll just focus on. So let's focus on something weird.
This is the Lynn Cox water temperature report. Lynn, the water temperature is 0 this morning, 32 degrees Fahrenheit.
The danger to Lynn Cox in these waters is even greater than it might first appear.
Skin, of course, freezes at about 32 degrees, but the seawater here in Antarctica freezes at about 28 degrees. So it's possible for the skin to freeze and die even before ice appears on the surface. One of the things that's difficult to convey about this story is just how this feels. To take your bare skin and to put it in this water is to feel something quite like needles sticking into your fingers. It is already very, very painful. After only just a few seconds, there is really a sensation of burning after about 30 seconds. And the fingers are already becoming almost too stiff to move. The water here is at about 32 or 30 degrees. That's the water that Lynn Cox will be swimming in.
Good luck.
In a sense, everything that Lynn has done in 30 years comes down to this. "32 degrees, water that would kill nearly anyone in 5 minutes. Her goal is 1 mile, and that will take nearly half an hour." Dr. Gabriella Mioto is watching for signs of trouble. So she's about 6 minutes in at this point. How does she look to you?
Good. She's just flooding her legs, her fingers are together. She's just been real even all the way so far. So she's paying attention to directions. So she's very...
Gary. Straight up, man.
We're shore.
What's it? On that
Head
side.
that way. Head that way. Head that way. She wants to go to shore.
Okay.
Just minutes after it begins, it seems over. She's calling for shore. The water appears to be much too cold.
Wants to go to shore?
Yes, she's asking to go to shore.
In 11 minutes, it feels like an hour.
Imagine how long it takes to her.
4 minutes later, maybe out of sheer hope, Lynn badly misjudges how far she has traveled.
We're shore.
Right here.
Yeah, we ready to get Are you ready to get a mile?
She's asking if it's a mile, but she's only gone half that far.
We're at 15 minutes.
15 minutes.
She's getting cold. She's going numb, and from the boat it's hard to watch. Then, just as her team is prepared to take her out, we hear the last thing we expected. It's that laugh again. Something like a second wind or a second warmth is taking over.
Hey, Barry. You are, woman. There was a sudden like burst of energy. I think she realized she had so many more minutes to go.
She'll try to go the distance. She's about 21 minutes into the swim. Gives us about 4 minutes to go. The penguins are coming down from the glacier down to the beach. It almost looks like a welcoming party. Maybe they're coming to welcome her into the club. She's done it. That's all of 25 minutes. She's done it. And she's done better than she hoped. Measured by a navigation satellite, she has covered 1.22 miles. They get her back in the Zodiac and race to the ship, lying on top of her for warmth. On board, her temperature rises, and so does her sense of triumph. What's next?
Hot shower? And chocolate?
Those are her trophies. There's no gold medal for swimming the first Antarctic mile, no picture on a cereal box. Just the warm satisfaction that your place in the world is unique, and that your record is certainly safe.
Okay, now most of us would not live more than 5 to 10 minutes in those waters. Okay, and then she did fine, right, for a half hour. Only a handful of people evidently can survive something like that. So the question is, how is she different from the rest of us? And some of you guys are thinking, because she's fat, she's overweight. That's the reason why. Having a layer of fat certainly is going to help, but I mean, it's not going to help you for a half hour, that's for sure. If you were to drop me in those waters, I like to think that I can survive for 5 minutes. More than likely, I would probably have a heart attack and die within a few minutes. And just being fat is probably you can survive that maybe about up to 10 minutes, but that's the extent of it. Okay, so being fat certainly helps, but it's not going to help you for a half hour. All right, so the question is, all right, so training and conditioning, I like that. Devin, give yourself 10 points for that one. That's training and conditioning may help under the circumstances, and some other reasons that we will get into. Okay. The guy who has the world record in terms of cold tolerance is this guy. His name is Wim Hof. He's known as the Iceman. A couple of things about this guy: he's not fat, and unlike this woman, he's not gonna swim in water. He's just gonna dip, and then he will dip and stay. That's what he's gonna do.
The cold is an absolute doorway to the soul. There's so much unnecessary suffering in the world. We take pills, kill the symptoms, but not the cause. And apparently we cannot become happy, strong, and healthy? Hey, I know the way. The cold is merciless, righteous. It brings you direct in the depth of yourself. You're not thinking. Your emotions stop. You are just surviving. And it brings you in the purity of the physiology as well as the soul. And you get in a different plane than our conditioning. And that makes you a free man.
What's special about Wim is that he kind of has this mind over body control that's pretty phenomenal. When he is exposed to the cold, his body just physically reacts differently from a lot of other people.
Right now I'm holding 26 Guinness World Records and all related to extreme cold. My records range from staying in the ice for 1 hour 53 minutes in direct contact with the ice, running fastest half marathon barefoot, climbing Kilimanjaro in record time in shorts, swimming underneath the ice for the longest distance.
Wim is a very special person. He has an aura to him that is very positive energy, but what you can see when he begins to breathe, he has the ability to focus his mind and body together in a higher function than most can do.
I created a method. The components are breathing, mindset, and cold exposure. Gradual, non-forced cold exposure. And that's to optimize the mind-body connection.
Wim has figured out ways, namely through breath work and through exposure to cold, to take conscious control over aspects of his physiology that, for most people, they simply can't tune into and control.
The cold, my warm friend, it brings about a whole lot of more energy, and that together with breathing makes you so powerful. But then you lose your wife and it all rumbles down. 4 children I had with my wife, and I was to be with her forever. She was the love of my life. She died. She suicided. It's a black hole within yourself. It breaks your heart and you don't know why, but the train of a daily life is going on and you gotta catch up, otherwise you lose it. So I had to be there for my children. And yes, we created a new nest. My children made me survive in that time, but nature healed my wounds. The cold gave me a direct understanding of deeper breathing and how to heal a broken heart. Then I went and did all kinds of remarkable challenges. Apparently, they found it very remarkable and great and spectacular. So I came in contact with television. One after the other, they challenged me more. Hey, go swim 50 meters under the ice. Go swim 100 meters under the ice. Like Mount Everest in shorts. That led up that the scientists became curious. Hey, what this man is doing is not possible physiologically.
The science of what Wim Hof method does is one of the primary interests of my lab now, because it is so powerful and it's been shown to be powerful in the immune system. And we believe it will also hold some real potential for treatment of neurologic diseases.
And this breathing technique brings you right into the deepest part of our physiology. Anybody can do it. So you become the alchemist of your own chemistry. Let's do this. Just breathe in. And let it go. Fully in. We become alkaline. More oxygen is getting in toward all cells. Then the alkalinity makes the chemistry right in our body. And then we are able to take a last inhale after 30-35 of these breaths. Deeply in, letting go, and you stop.
The Wim Hof method is neither distress nor eustress thrilling. It's somewhere right in between where I believe adrenaline is high and cortisol is low, which gives the person who's doing the method this incredible feeling of well-being and control over their own physiology and mental state.
Why I teach this method? To show that with a simple method out of nature, we are able to tackle the greatest problems, which is depression, fear, anxiety, and pain. People with chronic pain. That's all unnecessary suffering going on, and all this industry is keeping on and say, yeah, that's normal, and I think that's sick.
If it turns out that non-ingestible approaches, such as breathwork or cold exposure, can approach some of the potency that medications can provide or have failed to provide, then it's quite possible that one can heal from the inside.
Guess what? We found the proof to tap into our body and mind, enabling us to become happy, strong, and healthy.
Okay, so training has something to do with it. That's something that somebody already mentioned. So Devin already mentioned that. Austin, give yourself 10 points as well. Being from cold climate certainly helps. significantly. So this guy is the world record. He was in water for 1 hour, 52 minutes, and 42 seconds. He was in iced water for that long. So he's got the world record. And he's not fat, obviously, and he wasn't swimming. So, so we'll look into it because it's interesting. So what do we know about heat? So we know that heat is a form of energy, right? That flows from hot to cold. So it's the energy in transit from hot to cold. So it's a form of energy that's going to flow from hot to cold. This is a book definition, from a high temperature region to a low temperature region. All right, so if there's temperature difference, there's going to be a heat flow. All right, so the temperature difference can be expressed in terms of Celsius or Kelvin usually. In the United States, we use Fahrenheit. Also, this is a summary of what we did so far. So we can also obtain heat as a result of the energy conversion process. Like the mechanical energy can get converted into heat, electrical energy can get converted into heat, so forth. Okay, so now there are 3 ways you can transfer heat. One of them is called convection. All right, so whenever you're boiling water, what you experience is called convection. So the question is, what is convection? So the convection is the transfer of heat in the form of the bulk movement of the fluid that you're looking at. All right, so what's happening is if you're boiling water, for example, when you heat water, just like air, it's going to become less dense. So it's just going to rise up, it's going to cool down, and then it's going to sink down. So you end up getting a circulation out of it. All right, so what causes the circulation is the change of density or buoyancy, the Archimedes principle. This is going to be responsible for that. So that's the convection. That's the convection. So the heat is going to get transferred by the bulk movement of the fluid. So that's the definition of it. Convection.
In the 1950s.
So speaking of convection, the hot air is going to become less dense. And so this guy made sure that he was below the fire. All right, at the bottom of the fire, below the fire. He was not above it because the hot air is going to rise up. So he didn't want to get cooked. Certainly that helped. That's one of the 5 reasons, the entire reason. Most of you guys noticed that. All right, so as far as the heating units are concerned, in the proper home design, the heating units are usually placed at the bottom of the wall. All right, so the hot air is going to rise up, and then it's going to cool down, and then it's going to sink down and rise up again. So you end up getting this artificial circulation. Cooling units, like the AC units, air conditioning, is usually placed near the ceiling or at the ceiling because the cool air is going to sink down, and it's going to grab the heat from whatever's in the room or inside the fridge. So, and then it's going to heat up, and then you end up getting a circulation again. So the convection is the way we heat. Yeah, Gustavo, give yourself an iPhone. Yeah, I got that.
Into a flammable gas. To use a fuel that doesn't easily change into a flammable gas. This way it won't burn until it's a few inches away from the face. Gas is a fuel that doesn't easily...
One of the kids, I don't know why he tried to do it during one of the breaks. And then it evidently didn't have the right sort of gas. So as he was trying to blow the fire, his face, his hair got burnt a little bit and this and that, but it was a learning experience. One of the magicians a couple of years ago was one of the mask magicians. He didn't realize that the gas got in between the mask and his face, so his face got burnt a little bit there. So that was a problem. So that's where stuff is kind of tricky. All right, so the second type of transfer of heat is conduction. This time, what's happening is the heat is getting conducted through the collisions of the molecule. So what's getting conducted is the kinetic energy of the molecules. All right, so this is a slow-moving molecule, and then it speeds up. All right, so blue means slow, red means hot. All right, cold, hot. So it just speeds up. So which means that the motion, kinetic energy, is going to get transferred through the collisions of the molecules. All right, so the conduction is the process whereby the increased kinetic energy is going to get transferred from one molecule to the next molecule through collisions. All right, so
we did this. You remember what happened?
So the number of factors will play into conduction.
This is a little funny.
Notice that this is a desert fox. They got huge ears. All right, what's the reason for it? You will of course say, well, they can hear better. That's all correct. That's the purpose of it. But you got to remember that the dogs usually regulate body temperature. All right, so they pant and then they also regulate body temperature through ears. So there's a forced convection that takes place, which means that the blood through heart pumping obviously is forced through the skin. And so the foxes have all these veins and capillaries on their ears. So which means that the blood cools down through them.
He only weighs about 3 pounds. He weighed 1.5 ounces when he was born. This is the smallest canine, and found in a desert area where temperatures reach 120 degrees. Of course, the wonderful thing about what we can do in a zoo is show animals that are nocturnal that you might not see if you've ventured to Africa, and animals that are a little bit more difficult to see. These ears actually dissipate heat. The blood circulates through the ear, allowing them to cool their body temperature down, and it helps them to hear because they hunt at night. It's so hot during the day, they actually have fur on the bottom of their feet. If you look right here,
Okay, so the fur at the bottom of the feet
bottom of the feet
is going to help protect the skin.
are furred to protect from the hot.
So the question is how? Okay, so that's another thing that we will focus on. All right, so let's talk about conduction and what factors play into conduction. All right, number one, the energy is going to get transferred through the collision of the molecules. All right, so which means that the kinetic energy is the one that gets transferred. The motion gets transferred from molecules. All right, so the number one contributing reason is the temperature difference. All right, so larger the temperature difference is, the more heat is going to get transferred. All right, the second contributing factor is the length between the temperature gradient, between two temperature regions. Okay, so let's unpack this one a little bit. It's the thickness of the material through which the heat has to go through. All right, obviously, when it's really cold outside, you end up wearing thicker outfits because you're trying to contain the heat as much as possible. The colder the outside temperature is, the thicker the outfit that you're going to wear. So L represents the length between two different temperature regions, or you could say that that's the thickness of the material that you're wearing. All right, so A is going to represent the exposed cross-sectional area. All right, so bigger the exposed cross-sectional area, bigger the exposed areas, forget the cross-sectional area. Bigger the exposed area is, the more heat is going to be lost. All right, so the duration matters. Exposure time matters. Larger the exposure time is, obviously, more heat is going to transfer. Lastly, how well the material conducts heat. This is known as thermal conductivity. All right, so these are the contributing factors. So we'll take each and every single contributing factor and put it into a single formula. So thermal conductivity is how well the material conducts heat. All right, so all these contributing factors make up a formula. So this is the exposed surface area, temperature difference. This is the duration, the exposure time. L is going to represent the thickness of the material that you're wearing. Okay, certain materials are better at conducting heat than certain other materials, obviously. All right, so silverware is usually made up of steel. Here's the reason for it. Silver is a very good conductor of heat, steel not so much. If you're using actual silver when you're eating, if you're eating something really hot, your hand is going to get burned. That's what it means. So it's going to heat up real fast. Steel is going to heat up fairly fast, but it's not going to heat up as fast as silver. Oh. Air is not a very good conductor. Steel is. The best conductor that I'm looking at, the heat conductor, is diamonds. Diamonds are forever. Obviously, they're also super expensive. Traditionally, I think this is more of a marketing thing. People, whenever they propose, I don't know, you're supposed to spend 1 or 2 months' salary to show your love and dedication to the woman that you love. I got news for you guys. Diamonds are not worth anything in reality. They're not like gold. Okay, they do have some kind of an artistic worth. Aside from that, they're not worth a thing. Okay, so if you can convince your woman to accept real jewelry at some point, that may work out better in case you guys need the money at some point. Because when you try to sell the diamond back to the jewelry, you're not going to get the same money back. All right. If you want to make an impression, if you're gonna buy a diamond using your 2 months salary, why not just have the woman experience the same sort of pain that you're about to experience? Why not just put the diamond in an oven, heat up the oven up to 400 degrees? All right, you stick your hand in it. 400 degrees, it's not going to burn your hand. You will feel the heat on your hand. You can keep your hand there just, I don't know, maybe 15, 20 seconds without feeling any sort of discomfort, and you can just pull it out. But if there's a steel pan, and if you touch the steel pan, you will feel the temperature immediately. You will feel the heat. It's going to burn your hand as soon as you touch it. All right, so which one is hotter? Is it the air inside, or is it the steel pan, pizza pan inside? Which one is hotter at 400 degrees? All right, so you know the answer, hopefully. They're at the same temperature, so which means that neither one is going to be hotter. All right, so you can keep your hand in there. You're going to be fine up to a few, I'd say half a minute or so. But if you touch steel, immediately it's going to burn your fingers. And both of them are at the same temperature. The reason is because steel is a good conductor of heat. So what happens to the diamond when you put it in an oven? Right here. So you want to propose, at the same time you want to make an impression, right? So take the diamond and place it on a plate, and then take the plate, put it in a 400-degree oven, And then pull it out, get on your knees, and let her grab the diamond. So what do you think is going to happen to her as soon as she touches the diamond ring? Just forget the ring for now. Just let her touch the diamond. Do you think her hand's going to get burned as soon as she touches the diamond? Most of you guys will say yes to that. Most of you guys are thinking, oh, as soon as she touches the diamond, she's just going to have a first and second degree burns. In reality, nothing is going to happen to her. Right? The diamond is a really, really good conductor of heat, which means that as soon as you take it out, it's going to be at room temperature. You put it into an oven, it's going to be at the oven temperature. If it's 400 degrees inside, it's going to be 400 degrees. The diamond is going to be 400 degrees. If it's 500 degrees inside, diamond is going to be 500 degrees. You take it out, as soon as you take it out, it's going to be at the room temperature. So that's what happens. Higher the conductivity is, the faster the temperature is going to adjust. That's the meaning of it. All right, so Chicago, fairly cold today. Just before the lecture, it was snowing here. Last week I was in Houston. It felt like the summer. It felt more like the Chicago summer than the Houston summer. It was fairly comfortable last week. All right, so it's about 32 degrees outside right now. 32 degrees is it's freezing temperature for water. Okay. 32 degrees in Chicago is considered fairly comfortable, believe it or not. We usually play soccer at 32 degrees in shorts because during the winter it gets really, really cold around here. All right, 32 degrees is okay. It's an okay temperature. You could go out and play soccer for a few hours and come back home at 32 degrees. But you would not think of swimming in 32-degree water because you wouldn't last more than 5 minutes. Why not? Okay, guys, just remember, human body temperature, the average human body temperature is 98.6. 98.6, I think, is pretty accurate. 98.6. So outside temperature is going to be 32 degrees, so which means that the heat is going to be flowing out of your body, so which means that you end up losing heat, right? Now, air is not a very good conductor of heat, so you're not going to end up losing heat that fast. As a result, you don't feel as cold while you're playing soccer outside. But if you're trying to swim in cold water and you're freezing, all of a sudden you look at the conductivity of water, the thermal conductivity of water compared to air is fairly large. And remember, your body core temperature is 98.6, outside temperature is 32, which means that you're going to be losing heat fairly fast in that water. Okay, and then all of a sudden this creates a dangerous situation. All right, so the temperature difference is important, the thermal conductivity is important. So those are two factors that we end up discussing. The other factor that I'm going to discuss is the exposed surface area. It's not the cross-sectional area, but the exposed surface area is the one that I'm interested in. NBA, the National Basketball Association, or the leagues. Notice that every single race just about is represented pretty much, with the exception of Eskimos. Okay, so notice that we don't have any Eskimo basketball players playing professionally. I'm sure they can play basketball, and part of the reason why they don't play professionally is because they're not that tall. All right, so the reason is why is it that they don't get to be that tall? All right, the reason is because being tall and big means you would have an extremely large exposed surface area. All right, so where they live, the temperatures tend to be extremely, extremely low. So the survival of the fittest demands that you cannot have a large exposed surface area. All right, they tend to be fairly small in size, and because it benefits a small size in terms of being able to survive climates like that. All right, so they don't get to be very tall as a result. And when it gets really cold outside, anything that happens is, not that you guys are physicists, automatically, instinctively, you know that you would just curl up. Animals do the same. The reason why you curl up because you try to reduce your exposed surface area as much as possible. In that sense, you can maintain as much heat, body heat as possible in terms of surviving harsh climates.
98.6 degrees is normal core body temperature. Dropping to 93, amnesia starts to set in. At 87, you lose the ability to recognize even your family. At 85, you lose consciousness and appear dead.
All right, so 98.6 is the normal body temperature. 93, amnesia sets in. And 87, obviously you have a hard time recognizing faces. That's interesting. And 85 is as far as you go before you lose consciousness. Okay, so your core temperature is going to drop fairly fast in water. So this is what happens usually.
Based on all that they knew, Lynn should be dead. Professor Bill Keating of the University of London is a pioneer in the study of hypothermia.
You brought Lynn here to London for experiments in your lab.
Yes.
What have you found?
Well, we were able to confirm that she can maintain stable body temperature with her head out of the water, and in water temperatures as low as 44 Fahrenheit. We've got one other person that we know can do that. He was an Icelander who swam ashore from an overturned boat.
One other person on Earth that you know of.
This is one reason we were so interested in Lynn scientifically.
What would happen to the rest of us? Look at this British military diver slipping into 50-degree water. The pain hits like an electric shock. His muscles fail, and if they left him in much longer, his heart would be next.
The whole beating of the heart goes completely adrift. Technical terms, ventricular fibrillation. And then you're dead in a matter of minutes.
So how does Lynn stay alive? Keating thinks Lynn has somehow trained herself to keep most of her blood at her body's core and away from the skin where it's exposed to the cold. But there is also something else. Call it her natural insulation.
She's got an extremely even fat layer going right down the limbs, and it's an ideal setup.
Can we talk about your body?
I guess.
You're obviously very powerful.
Yes.
Incredible stamina. How tall are you?
5'6".
If you don't mind my asking, what do you weigh?
180, 190.
And that is the key to your success.
It helps. I mean, if you look at the marine mammals in Antarctica, the whales, the walruses, the seals all have body fat to stay warm. Their blubber is very dense, whereas mine will be more like a cotton sweater. But I'm not going to be in there as long as they are.
Okay, so part of the reason why she's capable of surviving is, I think part of it is genetic. Her body obviously knows how to handle the cold. Part of it is training. And also they notice that she has a nice layer of fat, which is fairly uniform. So the thicker the material is, in this case, is fat, the longer it's going to take for the heat to flow. All right, so the amount of heat that flows is going to be inversely proportional to the thickness of the material that the heat needs to go through, right? So the fat is not a very good conductor of heat, so that helps her survive, in essence.
Based on...
So she got some genetic... Okay, so ash is not a very good conductor of heat. Okay, so that's the reason why those people were okay.
It seems it's...
Of course, I knew that. And I decided at my school, at the art school, that we should do firewalking at the end of the semester. And this was going to be a student's final project. It was like their final test or something. And I decided that we should break the world record, just go for 500 feet firewalking. And the school where I was working, this is, I don't know, it's a for-profit school. It was a private school, so this is also amazing advertisement for the school because there would be a lot of publicity for something like that. So I tried to sell the idea, and then at first they were really skeptical. I said, "Hey, this is 100% safe. Nothing bad is going to happen." I explained the fact that the ash is not a very good conductor, but there's an illusion of danger. In reality, it's not dangerous. Blah blah blah. And so somebody asked, "What if somebody falls?" I said, "Not a big deal. We will just shadow the person and just pull the person out. I mean, if you fall, the exposure time becomes a factor. So just pull them out. Not a big deal." And right across the street, we had the fire department anyway, so it wouldn't be a big deal. All right, so the people that I talked to all the way up to the president, they were okay with it, except the legal department said, absolutely not, you cannot do something like that. And does this mean that they know more physics than I do? No, because if something happens to someone, we will get sued. There's no question about it. I mean, you're dealing with fire, they didn't want to deal with it. The legal department didn't want to have anything to do with that. All right, so is it really safe to walk in fire? Did I kind of oversell it? Or can you get yourself hurt pretty badly if something goes wrong?
It seems it's physics that keep your feet from being flame-grilled and not mind over matter. Or is it? What about a mind unprepared? A mind unsullied by the certainty of science?
That's going to be a lot worse than that.
To find out, let's segue to the next stage.
What are you cooking? We're going to be cooking well, at the bottom of your feet. We're looking at the science of firewalking. Firewalking! Awesome!
Apparently, Adam would walk over hot coals to walk over hot coals. So Adam's ready for his trial by fire.
You can do it!
And remember, before Cary, Grant, and Tori took their first hot step, they knew they wouldn't get burned.
You gotta tell your feet.
My heart rate just went up a bit. Okay. But Adam knows nothing about the data and the technique of stepping lightly. Will he get across unscathed, or will those red hot coals fry his feet? Ah, yes. Apparently so.
Wow! That hurt a lot. I was going through my head. As I did it, walk, 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 this isn't so bad. Holy crap, this is pretty bad. Ah! Like that. That's about the thought process.
So it seems that it does matter what's in your mind, but only insofar as knowledge about technique and preparation go.
With no prep at all, I think I made a classic mistake of speeding up and digging my feet into the coal some more. Ah!
Yep, Adam's hard marching method meant some of the coals stuck to his feet, giving them more time to conduct their heat. Ouch.
Thanks, me.
And after a call home with the not so good news,
So I just walked on hot coals, and I burned the hell out of my feet.
let's break out the burn cream and get this myth wrapped up. It seems it's physics that keep your feet from being flamed.
Well, it's supposed to be 100% safe, but it's not 100% safe. There's a reason why no one has done a 500 feet firewalk. All right, number one, it's really expensive. Number two, a lot of stuff can go wrong. The problem with Adam is he ended up digging his feet too deep. But that's normal. That wouldn't be a problem, except when the ash gets stuck between your toes. Remember, this thing is still fairly hot. It's extremely hot. It's 400, 500 degrees, except it doesn't transfer heat as much or as fast. It doesn't transfer heat as fast. That's the way it should be explained. But if it's stuck to the skin, exposure time matters. The longer it stays on the skin, more heat is going to transfer, so you can get yourself burned pretty badly. So the technique is important. The longer the walk is, the more chances that something could go wrong, obviously. So this requires a little bit of practice. All right, the transfer of heat. The third way you can transfer heat is through radiation, which means that the heat is going to be transferred in the form of electromagnetic waves, and it's going to be transferred at the light speed, the speed. All right, so the portion of the electromagnetic wave spectrum responsible for heat is known as infrared. And when it comes to heat, the color is going to matter. The darker colors will transfer heat faster. The lighter colors will not transfer heat as fast. Reflective surfaces will not transfer heat that much, if at all.
Night.
Provides no ambient illumination.
It's scary.
Yet objects give off energy in the form of heat.
It would be amazing if you could see what's out there.
DeVille DTS thermal detection system with a head-up display projects images of the road ahead.
Beyond the range of your headlamps.
The all-new DeVille DTS, the world's first car available with night vision. The power of and, the fusion of design and technology. Cadillac.
All right, so heat is something that you feel on your skin, but obviously there's technology that makes it visible. Okay, so what causes heat? This is one of those weird things. Infrared region of the electromagnetic spectrum that you're looking at, whatever these charges, the molecules are vibrating within this frequency range. This is 1 trillion to 100 trillion times per second. The heat is going to be generated. So that's what happens inside the sun. And then it travels all the way up to your skin at the light speed. So what happens when it hits the skin, the electric field of the electromagnetic field just kind of vibrates the molecules in your skin. And then obviously the vibrations take place between these two numbers once again. This is 1 trillion to 100 trillion times per second. So the vibrations will be between trillion to 100 trillion times per second. So the molecules move back and forth like that. So, and it creates the sensation of heat on your skin. The first person who actually noticed this was one of my heroes. It's Ben Franklin, like 350 years ago, about 300 years ago. I mean, this guy was, in his own time, he was considered to be one of the best physicists. And this is before the discovery of molecules and before even the idea of molecules was born or introduced into physics. This guy was actually thinking in terms of something within the sun causing vibrations under the skin. Okay, so he could just visualize this sort of stuff. I was just stunned that he came up with a theory which is very close to the modern theory when I was reading his autobiography. This is amazing. All right, so the third way of transferring heat is in the form of electromagnetic waves. Electromagnetic waves travel at the light speed, so the heat gets transferred in the form of electromagnetic waves. How much heat that gets transferred is, once again, it's going to depend on the temperature difference. In this case, the temperature is raised to the 4th power. You don't need to know that, but just understand that if there's temperature difference, there's a heat flow. It depends on the exposed area. Duration is going to matter. Emissivity it depends on how well the material emits heat. And this, okay, so emissivity is going to be related to the colors. All right, so how well the material is going to absorb heat or emit heat. Let's put it this way. All right. So the darker the color is, the larger the emissivity is going to be. More reflective the surface is, the smaller the emissivity is going to be. Emissivity, once again, is related to how much heat is going to go through the material, how much of it is going to be absorbed, how much of it is going to go through. Everything is going to be multiplied by a constant, so you don't need to know that. It's known as the Stefan-Boltzmann constant. All right, so the only thing you need to know is, once again, the temperature difference matters. Exposed surface area is going to matter. The duration is going to matter. And how well the material absorbs or emits heat is going to depend on the color and the reflectivity, in essence. Okay, so there's confinement here that we need to focus on. Okay, so darker colors are going to be better at absorbing, and they're also going to be better at re-emitting. All right, so they will absorb and they will re-emit. Okay, so it gets emitted. Reflective surfaces are going to be fairly bad at absorbing and re-emitting. All right, so let's just focus on these terms because there's a bit of a discussion that needs to take place at this point. Okay, so it's 120 degrees outside. Okay, so it's 120 degrees outside. You're wearing something dark. What does it mean? If it's 120 degrees outside temperature is going to be hotter than your core temperature, 98.6. So which means that the heat is going to flow in, which means that you will heat up faster. So in theory, if you go by that logic, you're going to heat up faster. That's what it is. So it's not a good idea to wear something dark if it's really, really hot outside. All right. At the same time, it's not a good idea to wear something dark when it's really, really cold outside either, if you're thinking about it. All right. So it's like 32 degrees outside. If I'm wearing something dark, which means that the heat flows from hot to cold, my body temperature is 98.6, outside temperature is 32, which means that I'm going to end up losing heat faster. So that's also not a good idea. So the darker outfits is usually not very good in terms of maintaining a steady body temperature. What's good is the reflective surfaces. All right, so if you're wearing something reflective, all right, it's not going to heat up as fast. When it's really hot outside, a lot of that heat is going to get reflected. And when it's really cold outside, and once again, a lot of that heat is going to get reflected inward. Okay, so that's the reason why we have reflective coating on the stuff that we send out into space. All right, so if you're facing the sun, the temperatures are near 300 degrees Fahrenheit, so electronics will fry. If you're in the shadow of the Earth, the temperatures are nearly negative 300 Fahrenheit. So those are sub-zero temperatures. Once again, in order to protect the electronics, you need to have reflective surfaces. Okay, so as a result, the heat in the form of radiation is going to get reflective. All right, so which means that the inside temperature is not going to rise up as fast. It's not going to cool down as fast. That's what they do. And then you got this Omni Reflective. All right, so this is the sort of stuff that I usually wear when it gets really cold outside. Okay, it's usually fairly light. It's got a reflective coating on the inside, so it reflects the heat back in. It maintains the heat, and then it reflects the heat back into my body. So instead of losing heat, I end up maintaining a steady body temperature because of it.
Meet Wim Hof. For decades, he's trained his mind to help his body withstand the coldest conditions imaginable. He set 18 world records and baffled countless scientists with his ability to stay warm.
Is it hot out here? Or is it just me?
Wim has what he calls a mental thermostat.
I don't feel the cold right now.
Are you Wim Hof? No. No, you are not Wim Hof. That's why we created Omni Heat Electric. It's warmth at the touch of a button. Wim may never need it, but when you do, we'll be waiting. What you are about to see is real. There are no props. No body doubles. Just a man keeping himself warm with the power of his mind. And another man keeping even warmer with an electric jacket. Omni Heat Electric. Warmth at the touch of a button. Wim Hof uses the power of his mind to stay warm, no matter how cold it gets. But not everyone can harness the mental thermostat the way Wim can. That's why we created Omni Heat Electric.
Nice jacket.
Thanks. I pressed this button to keep me warm.
I press this button and that keeps me warm.
Omni Heat Electric. Warmth at the touch of a button. How do you define paradise? If you're Wim Hof and control your body temperature with your mind, it may well be a winter's day in the Arctic Circle. But if you're wearing Omni Heat Electric, tropical paradise is always just a button push away. Omni Heat Electric. Warmth at the touch of a button. Wim Hof owns 18 world records. He ran a marathon in the Arctic Circle with no shirt or shoes. He has a mental thermostat. Omni Heat Electric has a button.
Are you cold? No. Are you cold?
No.
Omni Heat Electric. Warmth at the touch of a button.
Phase transition. Okay, so let's get back to the same question as before. Wearing something dark versus wearing something light. Most of you guys guessed it correctly. Then if you're wearing something dark when it's really hot outside, you will definitely heat up faster. So it actually makes sense to wear something light, like outfit which is white, versus something dark like outfit which happens to be black. But this person will claim to be feeling cooler than the other person. So the question is, how? Is that just an illusion, heat-induced illusion, or is there any physics explanation for it? So that's what we will go back and investigate. All right, so the phases of matter, let's discuss that. According to classical physics, there are three. You got solid, you got liquid, and you got gas. According to our modern understanding of physics, you could come up with 5. All right, near absolute zero, you will get boson-Einstein condensate. That's when the molecules appear to be dissolving into waves. So the question is, waves of what? So we will not focus on that question in this course, obviously. And then at extremely high temperatures, like the temperatures inside the sun or the stars, you get plasma, which means that everything becomes ionized. All right, so from the way we experience reality, we will have 3 phases of matter. So we will have solid, liquid, and gas. Ice is going to turn into water. Water can turn into gas, the vapor. So that's what we got. So there are a couple of things that we will focus on. So notice that you put heat into ice, temperature is going to rise up. Heat goes in, temperature goes up. Heat goes in, temperature goes up. It's 0 degrees, you put heat in, no change in temperature, but the ice melts. And then once the ice melts, the heat that you put in is going to go into the temperature. So the temperature is going to rise up all the way up to 100 degrees. At 100 degrees, it doesn't matter how much heat you put into the material. There's no change in temperature. Instead, what happens, the water turns into vapor. It turns into gas. All right, so what happens to the amount of heat that you put in if there's no temperature change? Obviously, energy is going into the system, but it's not going into the temperature, which means that it's not going into the kinetic energy of the molecules. So if that's the case, heat that you feed into the system, where does that heat go? What's going on with that heat? All right, so there are 3 phases of matter. Let's just look at it from a molecular perspective. Far left, you got the ice, solid. You got water, liquid. You got gas. When it's solid, the structure molecules are within the structure. The molecules are rigidly attached, and they're much more compact together. Liquid, you usually have 2, 3 molecules are attached, and they're able to roll over the other molecules. So that's the liquid state. Gas, the molecules are free; they're not attached, and they're further apart. All right. So in the solid case, molecules are closely packed together. Liquid case, they're further apart. Gas, they're further apart still. So the spacing between the molecules increases when you go from solid to liquid, liquid to gas. The distance, relative distance between the molecules is known as the potential energy between the molecules. So further apart, the molecules are more potential energy that they have. So more energy is stored in them, in essence. All right, so larger the temperature difference is, the more heat is going to transfer, or by putting more heat into something, you can increase the temperature further. So if you want to increase the temperature of water by 10 degrees, you have to put a certain amount of heat. If you want to increase it by 100 degrees, you have to put in more heat. That's what it means. More massive something is, the more heat is going to require. A cup of water, boiling cup of water versus boiling a gallon of water is not the same. A gallon of water is going to require a lot more heat than a cup of water. So larger the mass is, the more heat is going to be required. Also, the amount of heat that goes in terms of causing a temperature change or phase change, is going to depend on the material itself, which is known as the specific heat capacity. All right, so specific heat capacity, there's a book definition. We're not going to use the book definition. Instead, we will get to use a commonsensical definition. So specific heat capacity is going to represent the amount of heat required to cause a 1 degree Celsius of heat change, temperature change. This is the book definition, so we're not going to use that. It's the tendency to resist any temperature change or tendency to retain initial temperature. All right, so it's almost like heat inertia, tendency to resist any temperature change, or resistance to temperature change, or tendency to retain initial temperature of a material known as the specific heat capacity. All right, so let me illustrate or demonstrate that. Look at the numbers on the far right. All right, so the numbers on the far right expressed in terms of calories per kilogram per degree Celsius. So just calories is something that you could relate to. And when you're looking at the numbers on the far right, notice that the biggest number is 1 on the far right, and the biggest number belongs to water, which means that the water is going to be the most difficult to heat up, and the water is going to be the most difficult to cool down. That's what it means. It's the resistance to change in temperature or tendency to retain initial temperature. So you will have a really hard time. The water is going to require a lot of heat to heat up, and it's going to require a large temperature difference for it to cool down. So it's going to be harder to heat up water. It's going to be harder to cool down water. That's what it means. So this specific capacitor represents the resistance to change in temperature or tendency to initial temperature. All right, so when you are heating something up, in this case ice, temperature is going to rise up all the way up to 0 degrees. Temperature rising up means that the amount of heat that you put in, the energy that you put into the material, is going to go into the kinetic energy of the molecules. So molecules will speed up. And at 0 degrees, you're putting in heat, but there's no temperature change, right? So if that's the case, what's happening to the heat? It's still going into the system, but it's not going into the kinetic energy of the molecules. Instead, the molecules are moving further apart. So which means that it's breaking up the molecular bonds. So it's going into the potential energy of the molecules. And then once the bonds are broken up, now it's in the water state. You put in the heat. Now what's happening is the heat that you put in is going into the kinetic energy of the molecules. So temperature is going up. 100 degrees, temperature no longer rises up. The heat that you put in this time is going to go into the kinetic energy of the molecule. It's going into the potential energy of the molecules, meaning that it's breaking apart the molecular bonds further, and the molecules are moving further apart. So it's going into the potential energy of the molecules under the circumstances. All right, so during phase transitions, the energy that you put in goes into the potential energy of the molecules. Molecular bonds are broken, it turns into liquid. Molecular bonds broken, it turns into gas. And then when you cool it down, the molecular bonds are formed. They're much more compact. The molecules are nearby. And then when you cool it down further, once again, the molecular bonds are formed. Molecules are much closer together. So the potential energy goes down. And so it becomes a much more compact structure. All right, so here's the temperature. Here's the amount of heat that you put in. Initially, the amount of heat that you put in, this is ice, is going to go into temperature. So temperature rises up, which means that the kinetic energy of the molecules will go up. Molecules are moving faster. You hit 0 degrees, the amount of heat that you put in at this point is going to go into breaking the molecular bonds, so it goes into the potential energy of the molecules. And then you put more heat in, it goes into temperature, it goes into kinetic energy. And then at 100 degrees, the amount of heat that you put in is going to go into the phase transition. Molecules are going to break further. And it goes into the potential energy of the molecules. So the amount of heat that you put in per mass during these phase transitions is known as the latent heat. L stands for latent. All right, so the definition of latent is the dictionary definition. I'm surprised that there's, I don't know how many years I've been teaching this. I think 1 or 2 people knew what that meant. One of the guys was an attorney, so it didn't surprise me that he knew the meaning of it. Latent means it's hidden. So this is hidden heat. Because when you heat something up, you expect a temperature change. And during phase transitions, there's no temperature change. So temperature remains the same, except the amount of heat that you put in per mass is going to cause a phase transition. So this is the amount of heat required to cause a phase transition, which is known as latent heat. So this is the amount of heat that goes in or comes out of the potential energy of the molecules. So that's all right. The term that we will focus on, the region that we will focus on is this region. All right, so if you want to boil water, okay, so a couple of things to focus on. This is a 1 kilogram of water, 1 kilogram of ice. All right, so if you want to turn ice into water, this is the amount of heat that you need to feed into the system. 80 calories of heat required to turn ice into water. When I say ice, we're talking about 1 kilogram of each. If you want to turn water into steam, it takes 540 calories of heat. So 80 calories of heat required to turn ice into water, 540 calories of heat, which is required to turn water into steam. Okay, so likewise, if you want to turn steam into water, you have to cool it down, which means that you have to extract 540 calories of heat from that system in order to turn into water. And if you want to cool it down into ice, you need to extract about 80 calories of heat out of that system, so it turns into water. It turns into ice. All right, so one of the things that you need to focus on here is 80 calories of heat per kilogram of water needs to be extracted from water for it to turn into ice. All right, so for example, it's November here. Started to snow. Temperatures are like 32 degrees, so it's at 32 degrees the water freezes. We got a bunch of small lakes around here, and it's fun to actually go jogging around the lake at night when it's really, really cold outside. And it's fun to actually go jogging in my shorts because these lakes start to freeze up. When they're freezing, what happens? They release this amount of heat per kilogram of water into the environment. So right near a freezing lake, it's actually fairly warm. So that's what happens. So this is the amount of heat which is being extracted or given up by the lake as it starts to freeze up. And so just by the lakeside, it becomes extremely warm. I don't care how cold the outside temperature is, it gets really, really warm around the lake. So you can go jogging just about every single night until the lake is completely frozen.
2, 3, 4. That's it! In the end, all 15 of them make the...
And what's happening here is it... Now what I didn't show... Now you just watch...
of over 800 degrees.
So this is molten lead, 800 degrees.
And that is very, very hot. And I'm going to put my hands in this molten lead for you. Okay? Now you just watch me. And surprise...
There's a reason why he's not getting burned.
Surprisingly enough, not a mark on him. I'm fine. Now what I didn't show you was what I was doing here.
So what he was doing on the side is putting his hand in water. So there's a nice layer of water on his skin. So the heat goes into vaporizing the water. Remember, it takes, 540 calories of heat that goes into vaporizing water instead of being transferred.
I do that.
Of course, the exposure time is important, so he just dips it in.
Do it every time and not hurt myself.
Because number one, water is the most difficult to heat up. Number two, the heat is going to go into vaporizing water. And then when it does vaporize, there's this layer of steam. Okay, so this brings us to the next thing. Sweating.
The skin is not just an
pulls you down.
inert coating. It is an active organ.
So the question is how?
Skin keeps the body cool. This heat-sensitive camera shows in red and yellow the hottest areas on a body in action. During heavy exercise, muscles generate enough heat to boil several cups of coffee. This heat would easily damage the internal organs unless the body did something about it. Just below the skin surface are 3 million temperature control units. These are the sweat glands, each a coiled tube 4 feet long, loaded with liquid. As the body heats up, the tube contracts, squeezing a droplet of sweat out onto the skin. As the sweat evaporates, it draws heat from the skin and cools the body. A body working flat out can expel 2 pints of sweat per hour.
All right, so how does sweating make you feel cooler? This is a question that we will investigate. So you get the sweat on your skin, and then when the sweat evaporates, you end up feeling cooler, right? So the question is, at what temperature does the sweat evaporate? A lot of people mistakenly think that this sweat is going to evaporate at the same temperature as the water boils, which is 212 degrees. No, the water vaporizes at 212 degrees. If the water were to evaporate at 212 degrees, it would just boil your skin. It would have first and second degree burns, guys. That's not the way it is. Evaporation usually takes place at any temperature above freezing. Evaporation is going to make you feel cooler. Evaporation is not the same as vaporization. They're not the same. Vaporization happens at 212 degrees Fahrenheit or 100 degrees Celsius. All right, so that's evaporation. That's vaporization. Evaporation happens at any temperature above freezing. So what is evaporation versus vaporization? Evaporation is a process when the more molecules leave the liquid state than returning the liquid state. So in the case where more molecules are leaving the liquid state, that's known as evaporation. If more molecules are returning to the liquid state, that's known as condensation. If equal number of molecules are leaving and returning to liquid state, that's known as saturation. So the evaporation is the one that we're focusing on. Evaporation is going to cool you down. Take a look at the numbers. These are the molecules. Okay, bigger the number is, faster the molecules are moving. Just think of it that way. So bigger the number is, faster the molecules are moving. You know that the faster moving molecules will leave the liquid state first, right? So this is the average number for the molecules. So that's going to represent the average speed of the molecules or kinetic energy of these molecules. So as soon as the faster moving leave, what happens to the average kinetic energy? Drops, right? Which means that the temperature drops. Evaporation is going to cool you down because faster moving molecules end up leaving the system before the rest. And with the faster moving molecules leaving, the average kinetic energy goes down, which means that the temperature goes down. So as a result, you end up feeling cooler. So that's what happens. All right, so wearing something dark is going to benefit you in extremely hot climates, provided that you have an outfit that looks like this. Okay, I don't know what the name of the outfit is. I'm just going to say this guy's wearing a man's skirt or something. And when you're wearing some dark, you're going to heat up faster, and then you will sweat. All right, so radiation is the reason why you're going to heat up faster. And then when you start to sweat, the sweating is crucial under the circumstances because evaporation is going to cool you down. So the inside is going to be hotter. Inside this clothing is going to be actually hotter at some point, more than likely outside. So this is going to cause a circulation. So the hot air is going to rise up. Faster moving hot air is going to actually sweep away the faster moving molecules from your sweat, which means that it's going to cause evaporation. Evaporation is going to speed up. And your body's going to feel cooler. All right, so it causes a convection inside. All right, so there's a convection going on. The hot air is going to rise up, so it's going to be breezy underneath. As you start to sweat, obviously sweating is going to cool you down. So as a result, this person is going to feel cooler than the other person.
Yeah, it's kind of like that. Sierra Mist. One shockingly refreshing lemon lime.
Good job.
What's wrong with this commercial? Has anybody seen anything wrong with this commercial? So it's really, really hot. And guess what? The dog decided that it was going to max out the AC system. You know, the dogs cannot sweat, so that's a good thing to do. It's amazing that most people don't see anything wrong with it usually. Some people do, but they have a hard time explaining what it is.
Brent Van Arsdale manufactures small demonstration engines that show off the unique capabilities of Reverend Sterling's invention. One of the engines runs on the hot air from a cup of coffee. But surprisingly, it also runs on the cold air from a bowl of ice. All it needs is a temperature difference to make it run.
All you got to do is keep one side hot and the other side cold. You can do that any place that you can keep the temperature difference. These things will run.
This Sterling engine can run on the heat from the palm of your hand. Brent Van Arsdale manufactures.
Okay, so if there's temperature difference, there's going to be heat flow. And heat is a form of energy that flows from hot to cold, right? Energy means capacity to do work, which means that you should be able to extract work from it, which means that you can take that energy, turn it into a force, and move something with it, in essence. So if it's that easy, why can't I drive my car by using the temperature difference between the coffee that I'm drinking and the inside temperature of the car? Why is it that this doesn't work in real life? I mean, obviously, if there's temperature difference, there's heat flow. Heat is a form of energy that could be converted into useful work, meaning that you can literally spin something with it, or you can move something back and forth. Okay, I'm not interested in this one. All right, so we talked about the zeroth law. We talked about the third law. We kind of talked about the second law. Zeroth law is there's no temperature difference, no heat flow. Second law is if there's temperature difference, heat flows from hot to cold. Third law says the absolute zero cannot be reached. And the first law is the one that we kind of didn't emphasize. Let's focus on first law. All right, so when you feed heat into the system, it's going to heat up, which means that the heat is going to go into energizing the system. So the heat is going to go into increasing the internal energy of the system. And by the amount of work which is done by the system, the internal energy is going to go down. All right, so when you put heat into the tires, molecules are moving faster, right? All right, so the heat is going to go into the kinetic energy of the molecules. And the molecules will start to push up against the boundary. And all of a sudden, if the volume starts to expand in the direction of the push, which means that the molecules are doing work on the boundary, which means that the molecules will slow down. Because they take some of their kinetic energies and they transfer the kinetic energy to the boundary, to the wall of the tire, in essence. As a result, it starts to expand, the volume starts to get larger. So the energy of the system is going to go up by the amount of heat that you feed into the system. And the energy of the system is going to go down by the amount of work that the system performs or does in like causing an expansion of the volume or something. All right, so this is known as the conservation of energy, or otherwise known as the first law of thermodynamics. According to the second law, the heat is going to flow from hot to cold naturally, okay, and it would never flow in the opposite direction unless you can force it to flow in the opposite direction. Okay, so naturally, heat is always going to flow from hot to cold. So it's a form of energy that flows from hot to cold. This is your heat. By using a heat engine, you can extract a little bit of work out of it. And so the heat engine is any engine that's going to take heat and that's going to convert it into useful work, like mechanical work.
Brent Van Arsdale manufactures small
heat engines or combustion engines, for example. Okay, so combustion engines use gasoline to, and then gas engines, electrical engines. Believe it or not, you also are a heat engine. All right, so you eat the food, it turns into calories, it turns into heat, it turns into mechanical energy, and then whatever which is not used up is going to get pushed out of your body, obviously. All right, your body just takes it and puts it out. Okay, so every living thing is a heat engine. It goes in, you are able to do a little bit of work using that heat, and the heat that you're not able to use is going to get put out in essence. So it turns into exhaust. Now the heat naturally flows from hot to cold. If you want to reverse the process, like if you want to have an air conditioner or something, then you have to do a little bit of work. So you're trying to keep your room at a comfortable 70 degrees when it's 110 degrees outside. What happens is you have an AC unit that's going to do a little bit of work in order to extract the heat from your room, and then whatever the work that it does in terms of extracting the heat is going to put everything outside of your room. So which means that the outside of the AC unit is going to be actually hotter than inside of your room. So this is what was wrong with this commercial. Outside of the AC units will be hotter than the inside of your room, because not only is it able to extract the heat out of your room, so that amount of heat which is extracted is going to be transferred to the outside of the AC unit, but also the amount of work required to extract that heat is also going to be transferred to the outside of the AC unit. As a result, the outside of the AC units is going to be much, much hotter than the inside of your room. Okay, also the back of the fridges, where the back of the fridges will be hotter than your room temperature, because not only the amount of heat which is extracted from your food is put out, but also the amount of work done to extract that food is also put out of the refrigerator in the back of it.